Yeah, welcome everybody to this presentation on the first part of Promotion's Work Package 2, where the integration of diode rectifier units into HVDC systems has been investigated. As the work of this part of Work Package 2 has been distributed among several partners, also this overview presentation is split into three different parts given by three different speakers respectively. So you can see the organizations are Siemens, which is now Siemens Energy, the Polytechnical University of Valencia, and the University of Strathclyde in Glasgow. So my name is Markus Zeller. I'm with Siemens Energy, and I will take care of the first part before handing over to Soledad Bernal Perez from UPV and later on to Li Xu from the University of Strathclyde. So having said that, let me give you a short overview on the different parts of this talk. In the beginning, we will consider an AC parallel connection of wind power plants, WPPs, to diode rectifier units, or DRU in short, in parallel to an existing HVDC link and also in parallel to an existing AC cable as well. In the second part of the talk, we will then consider a connection of DRU-based wind power plants to existing HVDC interconnectors, however then by means of radial grid structures. And finally, the integration of DRU-based wind power plants in terms of meshed DC grids, by example of a small 4-terminal network, is also discussed. Now let's begin with the first part that has been the task of Siemens, where, as I just said, the diode rectifier units are coupled with other technologies on the AC side. Here you can see the overall system that has been investigated. In total, 3 different technologies are used for exporting the offshore wind power, and all of them are coupled on the offshore AC rather than on the DC side. So these 3 systems are a so-called DRU system, a VSC system, and an AC cable system. The DRU system represents the diode rectifier unit as it has been developed by Siemens. As you can see in this example, it's used to export the combined power from several offshore wind power plants. However, each of them needs to be connected to its own DRU unit. Since the DRU itself is essentially an uncontrolled diode bridge, also some filters are required as well. It should be noted that here 66 kV AC cables are assumed for the offshore grid. Secondly, we have the VSC system that is, as you might say, a conventional HVDC link, as it is now existing already a couple of times in the North Sea. This exports the power of 2 offshore wind parks here in this example. However, you should note that the 33 kV voltage level is used since it is still considered the state of the art currently. As a third option, the wind power can also be directly exported by an AC cable via a transformer to bring it to the 220 kV voltage level for the respective AC grid then. So also to note is that we have 2 couplings, as it is mentioned by the AC parallel operation, of course. So we have 2 interconnectors here connecting these 3 systems. So the integration of the DRUs with these systems has been considered, since this is likely to represent one of the first integration scenarios for early steps on the offshore meshing. Of course, for such a complex system, a lot of different scenarios can arise in principle. However, due to the limited time span of the work package, we have restricted to follow a lean modeling approach. That means we have tried to find an optimum trade-off between realistic models and valid results, also with respect to the number of simulations that had to be carried out. Nevertheless, you might see from the list below that all different aspects and the most important ones have been covered in the investigations. So simulations have been carried out for both black start and energization topics, as well as for some severe faults on the DC or the AC side, where, for example, either the DRU or VSC units, as well as the cables could trip. And above all of this, of course, also the normal operation with the fluctuating renewable power import has been covered by considering load flow changes in any of the wind parks or systems. Turning to the overall control strategy, we focus now first on the parallel operation of the DRU and the VSC system alone. As you can see to the left, one constraint is that during normal operation, no active power flow should be allowed through the interconnector. This can be achieved by controlling the angle of the voltage phasor at the DRU connected terminals relative to that of the main offshore AC bus. And this angle control can actually be implemented by the offshore wind power parks themselves. On the other hand, the operation of the DRU requires some reactive power as well that should be provided by the offshore VSC converter. So in this way, the power factor of the wind power parks can be maximized. It has been shown that this is feasible to do this by adjusting the magnitude of the voltage phasor at the offshore VSC terminals, and this is something that is also quite common already today. One thing to consider is, of course, that the amount of reactive power that can be exchanged between both systems is, of course, limited by the ampacity of the interconnecting AC cable. However, we have found that a rating of 200 megavolt amperes, as it has been used here, is quite sufficient to do this. Now we consider the second part of the overall system, that is the parallel operation of the HVDC connection and the AC export cable. Again, only state-of-the-art controls are assumed here since we're talking about existing connections. So you can see the operational concept in this case looks like follows. The VSC is basically in a voltage droop control mode. However, the AC voltage is kept fixed in magnitude, while only the angle is controlled such that the active power flow through the interconnection is prevented. The offshore wind park of the cable system is also controlled in voltage droop control mode in order to compensate for the reactive power demands of the AC cable. As compared to the previous situation, the objective here is to prevent any power flow, both P and Q, through the interconnection under normal operating conditions. Bringing all of this together now, still the same constraints hold for both of the interconnectors. Also, the individual control modes of all units remain the same as before. The controls of the VSC offshore converter are slightly modified in order to accommodate requirements for both interconnections. That means the AC voltage magnitude has to follow some droop on Q, and also the angle will depend on the active power to coordinate with the wind power park from the DRU system. However, these changes are negligible and can be implemented quite easily by adjusting the control software. Yeah, finally some words on the safe energization, which is of course quite important for such an extended offshore system. We will not go into details on the exact sequences here, but as you can see, the whole energization process is basically done stepwise and driven from the offshore VSC converter, which in turn is fed from its own onshore side. Generally speaking, the DRU units need to closely follow the energization of the VSC system and are connected in a staggered way to minimize the transients. The AC cable system, on the other hand, can already be energized from its own AC side, but before connecting these two parts, the DRU plus VSC system then needs to synchronize its voltage phasor to that of the AC system, of course. Let me quickly summarize the contributions of this part of the talk. So, a parallel operation of DRU, VSC and AC cable connections has been proven feasible, and only some smaller changes to the control and protection software are required for this, but no major changes to existing transmission assets is required in order to make the overall system work. So this statement is also backed by the fact that in all of our investigations, only state-of-the-art signaling has been used to control the load flow, and all has been done on a non-time critical basis. That means essentially that existing wind park connections by either AC cable export or using VSC links can safely be mixed with low-cost DRU connected wind parks, and the necessary reactive power can be supplied by the VSC. So this concludes part 1 by Siemens Energy. The speaker for the next part will now be Soledad Perez from UPV. Thank you very much.
Thanks, Marcus. The previous part of the presentation has shown the capability of DRU's AC side parallel connections to VSC, HVDC, and HVAC links. We are now going to present a DC side connection of DRU-based wind turbines to point-to-point interconnectors. The system considers two onshore plus-minus 320 kilovolts 1200 megawatts MMCs. As typical in interconnectors, there are half-bridge converters. The wind park consists of a diode-based rectifier connected to three 400 megawatts offshore wind power plants, as in the previous part of the presentation. The considered wind turbines are variable speed with fully rated back-to-back converters. In the model, AC filters and step-up transformers to reach 66 kV and submarine cables have been considered. The DRU unit is formed by three platforms. Each platform has 12-pulse diode-based rectifier with the corresponding AC and DC filters. The wind turbines include grid-forming control required to operate with a diode rectifier unit. The inner current and voltage loops are designed in a stationary alpha-barrel frame using proportional resonant controllers. The MMC stations are controlled in a standard master-slave operation. MMC1 in the picture is the master and sets the HVDC voltage, whereas MMC2 works on an active power set point. To implement the protection strategy during faults, necessary AC and DC breakers are included. We have studied both normal and fault operation of the considered system. To validate the controllers, several KPIs have been defined and can be found in the promotion project deliverables. Regarding normal operation, several active and reactive power set points have been sent to the different converter stations. The considered set points include both changes due to power flow between the onshore stations and due to wind power being injected by the DRU. In the slide, changes in reactive power reference in MMC1. The system follows the reference with the KPIs within the defined limits. Once normal operation was shown with the considered controllers, a large number of faults have been studied, both in the AC and the DC grids. One of the main aims has been to minimize the number of DC circuit breakers required for safe system operation. Depending on the allowable fault recovery time, it is possible to operate the system without DC circuit breakers. The example shown in the slide corresponds to a DRU AC ring bus. The fault location is number 4 in the picture. Before the fault, the wind power plant is sending 1 PU active power to the system and the DC voltage is at its rated value. Once the fault is cleared, the wind power plant recovers full protection in less than half a second. During the fault, wind power plant AC voltage decreased to 0 PU and wind turbine currents reach their limits. When the fault is cleared, the wind turbine controllers ensure a smooth system recovery. Beside the results shown, a large number of studies have been carried out to show adequate control performance during changing power demand set points and wind speed. Moreover, the control system shows a good performance and recovery during AC and DC faults at the terminals of the DRU and both MMC converter stations. After these studies, the main conclusion is that DRU stations can be used to integrate wind power plants into existing or new interconnectors.
In this part, the operation of DRU in meshed DC grid is studied. This shows the system configuration. So the system contains a minimum mesh as well as a point-to-point DC connection, as you see here. We have 2 onshore MMCs, each connect to a separate AC grid, and we have 2 offshore wind farms, one connects through a DRU and the other through a normal MMC. For MMC1, it acts as master VDC controller, while for the onshore MMC2, it acts in PQ control mode. For the offshore MMC3, it establishes the AC network for the offshore wind farm 1, while for the DRU connected offshore wind farm 2, it has to establish its own AC voltage frequency as well as controlling its power generation. So various cases, including normal operation with wind power variation and onshore and offshore AC faults are studied. Start with normal operation. So the wind power generation at the 2 wind farms are varied. For the example shown here, the power generation at the DRU connected offshore wind farm 2 varies at 2 seconds. So as you can see here, during the wind power variation, the DC voltage and the power generation and the transmission are well controlled. In this case, offshore AC faults are studied. So faults on offshore wind farm 1 as well as offshore wind farm 2 networks are applied. For the example shown here, when there's a fault at offshore wind farm 2 connected through the DIU, the power generation is immediately reduced, while the master VDC controller MMC1 regulates its power transmission to maintain the VDC voltage to largely constant. So as you can see here, after the fault isolation, the power generation from offshore wind farm 2 can be quickly recovered, and the system goes back to normal operation very quickly. Onshore AC faults have also been studied. In this example, the fault applies at the master VDC controller AC terminal. As you see here, different control options, including the use of DC chopper on the DC terminals, active offshore wind farm power reduction, have been studied. So as you can see, for the example, when the fault occurs at 2 seconds, the master VDC controller will lose the ability to control to regulate the DC voltage. So the DC voltage rises. In the same time, when the DC voltage rises, the power transmitted through the DIU is automatically curtailed, as you can see from the top curve here. So this helps to maintain or to limit the DC voltage rise. When the fault on the onshore AC side is cleared, the power generation from the offshore wind farm 2 and the VDC voltage goes back to a normal operation very quickly. So to conclude, the introduce of offshore wind farm connected through DIU into mesh DC grid has no adverse impact on system performance. System responses during both normal wind power variation and onshore and offshore AC faults show similar results as DC grid using MMC. In the event of onshore AC faults leading to limited power transmission capability, DIU-connected offshore wind farm automatically curtails its DC power with the rise of the DC voltage, exhibiting inherent onshore AC fault rise-through capability. So this concludes our presentation. Thank you for your attention. For further questions, please feel free to contact us.